Hi everyone, welcome back to the channel where we unravel the complexities of AI. I'm really excited about today's video because we're going to build a game of snakes and ladder, and in the process we're going to learn reinforcement learning. In particular, we're going to learn about this algorithm called QLearning that's going to help us train our model to play this board game. Let's jump right into it and see how this works. So the goal is for this agent to navigate this board and get to the finish line here in green. It needs to avoid the snakes and hopefully figure out how to use the ladder to get to that end position faster. As you can see, it's going to play multiple games where in the beginning it's going to just try to randomly move around and try to figure out what's going on in this game. In the process, it's getting rewards, and that's going to help it figure out the optimal path to go from the start position to the end position. All right, let's see, we're in game number 6. And it seems like it's figured out a path to go from start to end position in an optimal way. So this is what we're going to be building from scratch today. So let's get started. Before we build this game, let's learn a little bit more about what reinforcement learning is in the context of this game. So in this game, what you have is an agent. The agent has a set of actions it can do. It can basically, at every position in the board or every grid point, it can move left, it can move right, it can move up, or it can move down, right? So these are the set of actions that the agent can take. The agent is playing this game, or it's in this environment. So every time the agent does an action and interacts with the environment, its state changes. Like, so if it started here and moved right, you go from 0, 0 position to 1, 0, and it also gets a reward, right? So if the goal is to move from the start position to end position, quickly, and if it ends on the snake, it might get a large negative reward. Whereas if it ends up on the bottom of the ladder, it's going to get a big positive reward, right? So by interacting with the environment, the agent updates its state, and it also gets some reward. And the way this reinforcement learning works is the agent plays this game or interacts with the environment multiple times, and through trial and error figures out what the rules of the game are. What's really interesting about reinforcement learning is that there are a lot of analogies with how humans learn. Also, other intelligent animals learn. I have a dog, and the way we train him is by giving positive feedback, or in his case, giving treats, right? So that's his reward, and he very quickly learns to do certain tasks because he's very reward motivated. Reinforcement learning has been used to solve a number of really complex problems. Recently, DeepMind used reinforcement learning to beat the world's best Go player. It's also been used for natural language processing tasks. In fact, InstructGPT or ChatGPT was fine-tuned using reinforcement learning. If you kind of go to their blog, what it says is, to train InstructGPT models, our core technique is reinforcement learning from human feedback, a method we helped pioneer in our earlier alignment research. This technique uses human preferences as a reward signal to fine-tune our models, which is important as the safety and alignment problems we're aiming to solve are complex and subjective and aren't fully captured by automatic metrics. And this is really important. And there's this another blog by Cameron Wolf that I highly recommend, and he talks about this. In this case, we cannot apply a loss function that trains the language model to maximize human preferences with supervised learning. And why is that? Well, the score that we get from human is a bit of a black box, right? So there isn't an easy way to create a loss function. We can't just back propagate a loss applied to the score through rest of the neural network. So you can kind of see why reinforcement learning is used. It's also used in robotics to train robots. It's used for autonomous navigation in autonomous vehicles. It's used in recommendation systems, like if you're using Netflix and you're watching videos, and the system is kind of learning the types of videos you like, and it starts recommending things that are closer and closer to what you enjoy. It's also used in supply chain management and logistics. So there are a lot of different applications for reinforcement learning. Today we're gonna build a game and try to understand reinforcement learning. So we're gonna build this game in 3 steps. First, we need to create and render the board game. Another really important part about training a reinforcement learning algorithm is building some sort of reward system, because the goal of the algorithm is to maximize this reward. We also need to tell the agent, like, when it takes a particular action, what the next state is going to be. So we're gonna define that as well. And finally, we're going to implement an algorithm called QLearning to train this model and help the agent figure out how to navigate the board. All right, let's get started. So the first step is to define a function to build this board. We're just going to use matplotlib. Essentially, we're going to read an image file that has snakes and ladder, and this is what it looks like. And as you can see, we've pre-built this board. We're going to also add a robot, and all we're doing is essentially defining a grid size that's 4x4, and we're just given a particular board position. It places the robot icon at that location, and yeah, we're also creating a caption that indicates the current state. And let's just see this in action. It's really easy to use, so let me close this out. Let me run this function. And so if we just say render board game position, and position equals 0, 0, it just renders this, right? So I can move this anywhere else. So if I move 1, 0, it's here. If I move to 3, 3. Okay, so at least we've created something that allows us to visualize where this agent is in this board, and it also displays this state here. And if you might be wondering how I made this this image, I essentially used DALL-E. All right, this snake looks a little bit scary, but yeah, this is how you can actually use ChatGPT to help you build a different version of this game. The next step is to define the reward and the next state. So if this agent were to take an action like move to the right, we want to know how much reward it's going to get for that particular action, and then also what the next state is. All right, let's walk through this. So this function takes in board position as the input and an action, and this action could be, we define a set of possible actions here. So 0 means you move left, 1 means move right, 2 means move up, and then 3 means move down, right? And we know that the grid size is 4x4. We also need to kind of define where this ladder is. So ladder bottom is at 2, 1, ladder top is at 3, 2, snake head is at 1, 2, and snake tail is at 0, 1, right? Later on, we can add, build a more complex game with more snakes, a lot of snakes, and a lot of different ladder positions. For now, we just have one snake and one ladder. And what we're going to do is we're going to calculate the new board position. So if you start at, let's say, 0, 0, and you move to the right, it basically calculates what the new board position is, right? So in this case, it would be 1, 0. We want to also make sure that the agent cannot go outside of the board, so it basically confines the agent within this 4x4 grid. And then what we're going to do is check for these special positions. So if the position is at the ladder bottom, we want to automatically move the agent to the ladder top, right? And then if it's at the snake head, then it's going to move it back down to snake's tail. And then we're also going to define rewards. So there's a positive reward for finding the ladder. There's a negative reward for hitting the snake. There's also a large positive reward for reaching the endpoint, right? So if you reach 3, so this is 0, 0, 1, 2, 3. So if you reach the state 3, 3, 3, you're going to end up with a large positive reward. And then a standard step has a negative reward because you don't want to be wandering around the board. Yeah, so basically, let's see how this works. So let's say you were at 1, 1, and then you move to the right. Let's see what happens. 1, 1, and you move to the right, which is 1. You're gonna go to 3, 2, right? So instead of going here, you actually climbed the ladder, you went up here, and you got a positive reward of 2, right? So this is really important. As we saw earlier, the way that our reinforcement learning works is the agent takes an action in the environment, it moves to a new state, gets a new reward, and uses this to figure out an optimal path to maximize the rewards here. Before we build the QLearning algorithm so that the agent optimizes the path from start to finish, let's just look at what happens when you randomly kind of take an action to move the agent around the board and see what kind of rewards we end up with. So here we start the agent at 0, 0 position. I'm initializing the reward to 0. I'm going to render the board first, and there's a slight time delay so you can see what's going on. If the agent ends up at the finish line, then the game ends. And we are going to randomly pick which direction to go, right? So random int between 0 and 3. Remember, 0 means move left, 1 means move right, and so on. And then we're going to use that function that we created earlier, which basically, given a position and an action, it tells you what the next position is and what the reward was for the action you took. And then we're just going to clear the output and then update the position and add up the reward. Let's look at what this looks like. So we're going to do this over 30 iterations of 30 actions. All right, it's kind of just randomly moving around, and hopefully within that 30 steps reaches the endpoint. Anyways, you can see that the total reward it ended up getting for wandering around the board was -28. So this hopefully gives you a little bit more context once we start writing the algorithm to maximize the reward. All right, so before we build that QLearning algorithm or code it up, let's try to understand how this works. So essentially for QLearning, what you're going to do is you're going to list all the possible states that this agent can be at. So in this case, this board is 4 by 4, so there's 16 different states. And then at each state, or it can take 4 different actions, right? So it can move left, right, up, or down. So we're going to create this, essentially a lookup table that for a given state and a given action, we're going to come up with this value, so Q value, that's going to help us figure out what is the optimal path this agent needs to take to get from start to finish. And in the beginning, we're not going to know what these values are. So we're going to initialize everything to 0. The way this algorithm works is we have some initial state that the agent is going to start with. So in this case, we're going to start it as 0, 0. It's going to pick an action by looking at this Q table, and it's going to pick an action that maximizes the Q value, right? And then once it picks that action, it's going to observe what the reward is and what the next state is. And then based on this, we're going to update this Q table again. And we're going to update this Q table using what's called Bellman equation. I've reduced this to a simpler form. There are lots of other things we can do, like add a discount factor, which is how much of the future value of reward you wanna take into account. In this case, I'm going to make it really simple. And so the update rule is you're going to just look at what reward you got in the current by taking the current action. And then you're going to add that with the maximum Q value for the next step. So the highest returning action at the next step, right? And this is what we're going to use to update this Q table. And what we'll find is as this agent kind of moves around this table and updates this Q table, we're going to end up with an algorithm that essentially picks a optimal policy. And policy essentially means, given a state, what action do you need to take? We're going to create a Q table, and remember there's 16 board position or 16 states, and we have 4 different actions, right? Move left, move right, move up, move down. We're going to start at 0, 0, which is the bottom right, and then we're going to finish at 3, 3, which is the finish the endpoint. And the goal for this reinforcement learning algorithm is for this agent to figure out the path that gives the most reward. This is what the Q table roughly looks like. It has the grid state, it has all the actions that the agent can take, and then there's going to be a Q value associated with this, with each state and action pair. And for the QLearning algorithm, here are the basic steps we're going to take. So the agent picks an action to execute from the current state, right? We'll use this thing called greedy policy, meaning we'll pick the action with the largest Q value. And if the Q values are the same, which it's going to be in the beginning, remember we're going to initialize everything to 0 because we don't know what the Q table is. It's going to pick the action at random. And then once it performs the action, we're going to observe the reward and the next state from playing the game, right? And then we're going to use that reward and the next state information to update the Q value based on this Bellman equation. And this Bellman equation for now we're going to use a simpler version of it. And so if there's no entry in the table for the current state and action pair, we're going to add those entries and we're going to set the Q values to 0. So essentially, we're going to kind of build up this Q table as we go. And then we're going to update the Q value for the current grid state and action pair. And the way we do that is we just add the reward that we got plus the maximum value, the Q value for the next grid state, right? And then we're just going to go to the next position and then we're just going to repeat. So yeah, this is a relatively simple algorithm, and we're going to see how, even though it's relatively simple, it in very few games figures out the optimal path to go from start to finish. All right, so the first thing to do is to initialize an empty Q table. So we're just going to make a dictionary. This is going to be our initial state. So position is 0, 0. For each position and an action, we're going to initialize the Q table to 0 because in the beginning we don't know what because the agent hasn't played the game to know what the Q value is, right? So let's just do that. We can take a look. Right, so for a given grid state and action pair, the Q value is 0. This is what this means. All right, so for the QLearning part, I'm actually going to code this up slowly so that we can kind of understand what's going on. So the first thing we need to do is we need to loop over some number of games. We're going to say 10 game runs, right? And then each game ends when the agent reaches the green cell. Right, so maximum games is 10. Episodes basically just mean which game you're playing. And then while the episodes is less than max number of games. So this is an iteration, right? So it's going to play your games multiple times. What we're going to do is we're going to first render the current grid state. Right, so let's start by clearing the display. And then we're gonna render the game board position, right? So right now, if you were to just see what's going on, you're probably not gonna see a whole lot. It's just gonna render it 10 times, and that's basically it. Let me stop this. So then we need to say if we reach the green cell, right, we need to reinitialize the game, meaning if position equals 3, 3, what we're gonna do is we're just gonna, let's say we're gonna pause for a little bit just so that you can see what's going on, and then we're gonna update the episodes, and we're gonna reinitialize the agent back to the starting position. So nothing is going to happen here because we still haven't taken any action to move the agent around the board. What we're going to do is, remember the algorithm, we have an initial state. We pick an action by looking at the Q table. Let's do that. So select an action. Now, so we need to write some function that, given a current Q table and a current position, it's able to tell you what is the best action is. we've kind of defined this function that looks at the Q table and looks at the current state or the current position, and then returns the action with the highest Q value, right? So if we were to run this function on this particular Q function and start position of 0, 0, you can see that all actions, whether it's 0, 1, 2, or 3, all have Q value of 0. So in that case, it's going to just choose one of the actions in random. So it does random choice. We can see this in action below. So if you were to say, okay, what is the best action here? It's not defined. So 1, it's probably going to keep changing. But okay, I just artificially updated this Q table. And if I were to ask what is the best action, if I were to look at this Q table and if I was in position 1, 0, then based on this, if I were to just look at it, I should be able to say, oh, okay, the Q value is highest for this position action pair, so 1 should be the action we should choose. What 1 in this case means moving right. So let's see if this algorithm does it. There you go, it does, right? So all right, so we've chosen, we've selected an action given a Q table and given a certain position. And remember this, we haven't even built this Q table out. We just, in this case, we just built the Q table for the starting position, right? And we initialized it to 0. Hopefully by the end of this game, we have Q values for every state and action pair. All right, so the next thing is to observe the next position and the reward. And remember, we've already kind of written this function right up here. Get next position reward, get next position reward. Once we have that, we're going to see state action pair is already included in the Q table. If not, we're going to add that and initialize it to 0. So add new position to the Q table if not already there. So move left, move right, move up, move down, right? So all these state action pairs are initialized to 0. And then we're going to finally update the Q table for the current position using a version of Bellman equation. So I put in quotes. So we need to figure out, remember what we need to do is we need to figure out the max value of Q for the next, so the highest returning action at the next step, right? So Q max is max value of Q for all the next steps. So basically, what is the next step? So you have 4 different actions. So this one, max value and Q value for the next position, and there's 4 different states. All right, awesome. And then finally, what we need to do is we need to add the current reward. Right, so, position is the current reward that we got from taking that action, and then the max value of Q for the next position. And then what we're going to do is we're going to update to the next position. That's it. So this is our QLearning algorithm. I'm going to show you what the Q value looks like right now before we play the game, and we'll look at what this Q value looks like once we play the game. All right, so let's run this game like for 10 times and see how the agent figures out how to move around the board in the process through trial and error. All right, kind of moving randomly. All right, so I think now it's stabilized. All right, so now let's take a look at what this Q table looks like. Wow, it's a lot different than what we had earlier, right? And this Q lookup table is how this agent kind of navigates, and we can kind of essentially follow this path, right? So if you start at 0, 0, we pick an action based on what Q value is the maximum. So in this case, it's 1, right? So this is going to move to the right. when it moves to the right, it gets to 1, 0. So if you're 1, 0, it's we pick the action with the highest Q value. So in this case, it's again moved to the right. So it's going here, here. And then, so you are at 2, 0. So if you're at 2, 0, it says, okay, the highest value is, for the action is 2, right? So 2 is move up. So when it goes up here, it automatically ends up here, which is 3, 2, right? So if you're at 3, 2, so 3, 2, again, it says the Q value for the highest one is going up, and this is how it ends up here. All right, so I've added a way to track both the current episodes as well as the total reward, so we can see if it's learning as it's playing the game. All right, so it's gonna kind of wander around in the beginning. Right, got a reward of 2 in that particular game. Still wandering around. Got a large negative reward for wandering around the board. Getting better at navigating the board, and it has played about 4 games now. Reward keeps increasing. It seems like the reward now is basically constant. I'm going to play a few more games. All right, and we can kind of look at the updated Q table. I also wrote a little function here to print the optimal trajectory it found given a Q table. And also to kind of visualize that. Let's look at it. All right, so this is what it found as the optimal trajectory to go from the start position to end position. All right, so hopefully by building this really simple game, you learned a little bit more about how reinforcement learning works and how you can use reinforcement learning to solve really interesting complex problems in the real world. Something that's really interesting is a combination of deep learning with reinforcement learning, and we'll cover that in future videos. And if you liked today's video, please subscribe to our channel and also give us a thumbs up. Thanks.